And we are now recording. Let's start from the current slide. Actually, we did a slide. Or did we? I don't think we did. I think we were at the beginning, weren't we? Okay. So we'll go from current slide. Okay. What's that?
So we finished the sum and difference, 5.4.
What about 5.4?
So we finished 5.4.
Yeah, we just did finish, and we're going to start at the beginning. I had a mark in the book, but that's from the last time I taught it. I didn't realize that I had taken that off. All right. We are still, okay, before we get to that, let's cover just a couple things. I know right at the beginning of the term, we talked about safety. Today may be one of those times that we might need to call upon one of those. We're under a tornado watch or warning? Watch. Okay. So if we hear those sirens go off, it may not be tornado. It could be severe thunderstorms or something else. If we hear them go off, just a little quick review of what we're supposed to do. We go out of the door here, hang a left, go down this little half flight of stairs right there, okay? Hang another left, go down one more complete flight, and then when we get to the bottom floor, the lowest point, almost the lowest point of the building, right below here, that's almost set up the same way as here. There's two restrooms there. They're pretty safe places. They're interior, lowest level, okay? Close walls, lots of strength there, okay? You go down about 2 or 3 more steps, and then there's the dean's office. That's another close space, close walls, and not a bad place to be. And it looks like I'm not recording. And I don't know why. There we go. It was recording, now it's, then it wasn't, then it was. Here's Josh. Okay. So we go down one more flight of stairs. The restroom's not a bad place. The dean's office wouldn't be bad, but it's usually locked up, don't break in. Okay. After that, there's a classroom, room 160. That's a large room, but the back wall, the most interior wall, very, very solid wall. Soil behind it, that's very safe. So is the restroom. Anything on that side, the back wall of that is safe. The walls are safe. The corners are the safest place. And then, so that would be a 160. Just past that, you go into the library, and there's a little computer lab there. That's safe because that's against that back wall, soil against it, and you lots of corners. 4 corners, they're closed walls, pretty safe. The room right next to that, I call the reference room. It's a little bit larger. It's okay. Again, back wall is very secure. Any of the corners are quite secure. Don't go any further in the library because then you're on the exterior of the building. Okay? The other place, and probably the place that most people will default to, is the hallway. The reason I say that, if we do have severe weather, the likelihood of losing power is pretty great. And if we lose power, everything's dark. The restrooms are dark, the classrooms are dark, these offices are dark, anything's dark except the hallways have emergency lighting. So that probably is where we'll congregate if we do have a weather emergency. So, lead the other students who are coming in after. Yes, sir. Okay, yeah. No problem, we're just getting started. Okay.
The explanations.
Okay.
I'm sorry.
No problem. Okay.
Where is your office?
Huh?
265.
It's 265.
Okay.
Yeah, it's across from the orientation classroom. But you said you did that on mine, I think. Okay. All right. So, that's where to go if we do have a weather emergency. And stay together. I'll take the roll book, call roll. we try to make sure we account for everybody. After that, you can mingle among friends or whatever. All right, so only other thing is what's next Tuesday? Voting, election day. Please vote, everybody. Make your plan. I mean, don't just leave it to chance. If I left it to chance, I wouldn't vote because I get off work here at 7:45. The polls close at 7. So I can't vote on my way home. I have to vote on my way in. Okay? Jake's here. Okay. Good deal. All right. Any other statements? I don't guess so. Okay. Then if no other questions, let's proceed with, in Chapter 5, this is the last section, 5.5, multi-angle and product to sum formulas. Okay. Now, I think when I led off the last section, I said these are things you sometimes use, but not some of them you're seldom use. I was wrong. I was thinking this section. The ones in the previous one, the multiple angle formulas, those kind of sum angles and difference angle formulas, those you do use quite a bit. So get those down, okay? Some of these you use a whole lot, some of them you hardly use at all. And I'll try to point those out as we get to them. So, last section in analytic trigonometry, multiple angle and product to sum formulas, okay? So what we'll do, our objectives here are to use multiple angle formulas to rewrite and evaluate trigonometric functions. We'll use power reducing formulas to rewrite and evaluate trigonometric functions. And we'll use half angle formulas to rewrite and evaluate trigonometric functions. Any clue that we are interested in rewriting and evaluating trigonometric functions? Okay. Then we'll use product to sum formulas and sum to product formulas to rewrite and evaluate trigonometric functions. And then finally, we'll use trigonometric formulas to rewrite some real-life models and be able to solve them, or at least evaluate them. Any questions? All right, let's start with the multiple angle formulas. I'm not going to give them to you to begin with. I want you to remind me of our sum angle formulas. You remember those? Let me get my pen set up. What was that? Sine of u plus v. What was that? Sine u cosine v plus cosine u sine v. Like I said, you will use these periodically. Let's do our cosine of u plus v. Cosine u cosine v minus sine u sine v. All right. Here's Walter, right? Okay. And let's do tangent. Well, we don't use as much. Does anyone remember how that goes? Okay, over. That's it. I can't write. There we go. All right. Just a little review with a reason. What if u is equal to v? What if u is equal to v? What does this one say then? Sine of? Say again? U plus u. Happy birthday. U plus u is? 2u. Okay. All right. Okay. Now, what does this give you then? Sine u. And if u is equal to v, cosine u plus, and if u is equal to v, cosine u sine u, which is, of course, 2 sine u cosine u. Ha! So sine of 2u is twice sine u times cosine u, right? All right, let's do the same thing for cosine. What if u is equal to v? What would this be? Cosine, happy cosine 2u, okay? And that would be cosine u cosine u minus sine u, which would be cosine squared u minus sine squared u, right? Cosine u times cosine u is cosine squared u, right? Sine u times sine u is sine squared u. So there's a cosine 2u is that. Now, there are a couple more ways of writing that. What does it look sort of like? It looks like a Pythagorean identity, except it has a minus there instead. So let's take the Pythagorean identity, because it has sine squareds and cosine squareds in it. So let's start with, give me another way to write sine squared u. Using 1 minus cosine squared u, okay? So let's plug that in here. This would be cosine squared u minus a 1 minus cosine squared u, and that would be cosine squared u minus 1, minus a minus is plus cosine squared u, so that would be 2 cosine squared u minus 1. There's another way to write cosine of 2u. Or we could solve this for cosine squared u, and what's that? Cosine squared u is equal to 1 minus sine squared u. Now let's plug that in this one, and that would be 1 minus sine squared u minus sine squared u, and that would be, I'm going to write it up here, 1 minus 2, I can't write, sine squared u. So you have 3 different expressions for cosine 2u. Okay? 1 for sine squared, sine 2u. Okay? 3 for cosine 2u. How about tangent 2u? What would that be? If u is equal to v, this would be tangent 2u is equal to tangent u plus tangent u over 1 minus tangent u times tangent u, right? Which would be what? Two tangent u over 1 minus tangent squared u. All right, good deal. So now we have one formula for sine 2u, 3 formulas for cosine 2u, and 1 for tangent 2u. And that's what they were going to do next, okay? So in this section, you'll study 4 other categories of trigonometric identities. Okay, I thought we were going to go right into it. The first category involves functions of multiple angles, such as sine ku and cosine ku. We've already done it for when k is equal to 2. Okay? Second category involves squares of trigonometric functions, such as sine squared u, and we sort of did some of those. The third category involves functions of half-angle formulas. I haven't quite gotten there yet, but you'll be surprised we really are very close to having that done too. And the fourth category involves products of trigonometric functions, such as sine u times cosine u. And you probably have a pretty good clue of where we get those two from what we've already done. All right. So here's the double angle formulas, which we just derived. Sine of 2u was 2 sine u times cosine u, straight out of the sum angle formula. Cosine 2u, on the other hand, had three ramifications. The first was the difference of their squares, cosine squared u minus sine squared u. The second is 2 cosine squared u minus 1. We actually did it third. And the other one was 1 minus 2 sine squared u. So all three of those are expressions of cosine of a double angle. Tangent of a double angle, again, just one expression of that. 2 times cosine, tangent of u minus 1 over 1 minus tan squared u. I can't talk. Okay. Any questions? So here we got, oh boy, every time we turn around we get more identities, don't we? Let's just keep spinning, okay? We don't have enough, do we? All right, now what do we do with these? Okay? For some reason, every time I move, okay. There, we got it back. So, can we solve this? 2 cosine x plus sine 2x equals 0. What would be your first suggestion? Where would you proceed from here? Anybody? Yeah, let's use a double angle formula for sine. So this will be 2 cosine x plus, and what was sine 2x? You just had it. What was it? 2 sine x cosine x. Okay? And that supposedly is equal to 0. Well, doesn't look like that made it much better, or did it? What would you do next? Anybody?
Take out the 2.
Okay, factor out a 2. That's easy. Anything else?
Take out a cosine.
Yes, let's factor out a cosine while we're at it. Greatest common factor. What's left in the first term? 1, and then the second term, sine x. And that product is equal to 0. And what can we do with that? Anybody? Anybody? If you have a product of two entities equal to 0, what does that tell you? Yeah, one or the other, or both, has to be 0. So this indicates that either 2 cosine x is equal to 0, or 1 plus sine x is equal to 0. Okay. Now, they didn't put any restrictions on what x could be, so we're going to have one of those with a general solution that can cover a whole bunch of possibilities, infinite number, in fact. So what's some possibilities for 2 cosine x equals 0? Where is cosine equal to 0? 2's never equal to 0, so where is cosine equal to 0? Yeah? All your half pies. 1/2 pi, 3/2 pi, 7/2 pi, 5/2 pi, all those, -1/2 pi, -3/2 pi, -5/2 pi, all those. So we can actually say pi halves plus n pi. Most of the time we put 2n pi for cosine, but because these fall at exactly your n pi apart, from pi halves to 3/2 pi is exactly n pi away. So every one of those is exactly, so we can just say it that way. The book probably says plus 2n pi, and then they do it for 3/2 pi and 2n pi. You come out with the same thing. Okay, it's just shorter to write this way. Okay, how about this next one? What would we do?
Subtract 1.
Subtract 1 from both sides of the equation, and that gives you sin x is equal to -1. And where is that true? You're absolutely right, -pi halves. So when x is equal to -pi halves, okay? You could have also said, why is it doing this? I don't know. Okay. You could have also said 3/2 pi, right? Because -pi halves and 3/2 pi are the same location. And then, how often does that show up? Not n pi, 2n pi. Because the n pi is going up at plus 1. So at 2n pi, it's going to be that. Well, guess what? That's also covered here. So both of these give the same result, and that's that one. Well, the second one doesn't give all those, but those all produce 0. That one produces the same thing. So it's either -pi halves plus 2n pi, or you could have written that as 3/2 pi plus 2n pi. But guess what? All those are covered by this as well. That's every half pi. These are your every other half pi. Okay, so that's certainly covered here. So pi halves plus, and for the life, this one covers every possibility. So you can write it like the book does, or you can write it just that way. So let me show you how the book does. By the way, there is a checkpoint following this, so you can certainly do your checkpoint, I'd suggest, as soon as you could after class is over. So begin by rewriting the equation so it involves functions of x rather than 2x. So they rewrite the equation. Yes, I'm glad they did that. Okay, then they use the double angle formula for sine and write what that is. That then enables you to factor out a 2 cosine x, leaving you a 1 plus sine x. That's equal to 0. So both of those factors have to be, or one or the other, has to be true. So if 2 cosine x is equal to 0, or 1 plus sine x equals 0, one of those has to be true. The first one you find at every half pi. They put a pi halves and 3/2 pi, but guess what? Those are exactly pi apart, so every half pi is going to produce that. So the short way of writing that is pi halves plus n pi. And then the 3/2 pi shows up again for the second one, same as the first. So you're covered if you just put pi halves plus n pi. Okay. They write it that way, which gives you exactly the same answer. It's just longer to write. Why write it the long way when you can write it shorter? Okay? Any questions? All right, that was example 1. And again, there is a checkpoint. Please do that. And before we go to power reducing formulas, there's also examples 2 and 3. So let's go back and do those as well. Example 2. Use the conditions below to find sine of 2 theta, cosine 2 theta, and tangent 2 theta. Well, here are the conditions. Okay, we're looking for sine 2 theta, cosine 2 theta, and tangent 2 theta. Okay, that's what we're going to be looking for. Here are the conditions. Cosine theta is equal to 5/13. And that's good anywhere between 3 pi halves and 2 pi. Okay, where are we talking about then? Where are we? Waldo, when you're between 3 halves pi and 2 pi.
The
Fourth quadrant. Is cosine positive in the fourth quadrant?
Yes.
Yes, so this makes sense. Okay? All right. So we know you're in the fourth quadrant and you know what the cosine value is there. All right. And that's all the data they give you. Okay. Now, hope you're not too surprised to know I suggest you draw a circle. And guess what circle I'm going to make this one? Probably not a unit circle, a 13 circle. You got it, because that denominator is your hypotenuse, which is 13. So we'll start with close to halfway. That's between 6 and 7. And halfway to 6 is 3, so there's 1 and 2 and 4 and 5. And halfway between 7 and 13 is a 10. That would be an 8 and 9, 11 and 12. Okay? Since we know we're in the third quadrant here, let's do the same for down there. Let's do that, a 6 and a 7, a 3, a 1 and a 2, and a 4 and 5. Goodness, my eyes are hurting me. So I got 7. Halfway to 13 would be a 10, so this would be an 8 and a 9, and 11 and a 12. Okay, so that's where you are. We know we're in the fourth quadrant. We know the cosine is x over r, right? So that's going to be 5, 1, 2, 3, 4, 5 over r. Somewhere down here. There is the angle theta. Okay? Right down there. Okay. Mine isn't drawn too well, I can tell right now. Okay. So, what you reckon we're going to have to do to come up with a sine 2 theta? What is sine 2 theta anyway? Remind me of that.
Sine times cosine.
2 times sine theta times cosine theta. Okay? Now, we already know what cosine theta is. We got that. If we only knew what sine theta was, we could then know what sine 2 theta is, right? Now, from what we know there, with that circle, now don't pay too much attention to where it is, I didn't draw it very well, but any idea how to get what sine theta is?
Use right triangle tree.
You say that again?
Use right triangle tree.
Okay, and what does that give you? We know this side, the adjacent side here, 1, 2, 3, 4, 5, is 5. We know this one right here is 13. That's how we got that angle. we have to figure out what this side is. Does anyone happen to know? If not, we can use good old Pythagorean theorem. And what would that tell us it would be?
Zero.
12, exactly. That would be 12. Now my picture doesn't show it because 5 squared is 25, 12 squared is 144, 25 plus 144 is 169. That happens to be the square of 13. So, if that's 12, then what's sine theta? Oh, only thing is I would write that as a minus 12 because in the fourth quadrant the y value is negative. So sine 2 theta would be 2 times what sine theta? Negative 12 over 13. And cosine theta we were already given is 5 over 13. So this would be negative 120, right? 2 times 5 is 10 times a negative 12 would be a negative 120 over 13 squared, which is 169, isn't it? You just did that with the Pythagorean theorem, so I'm pretty sure that's 169. Okay. How could we do cosine 2 theta? Remind me what that is. There are 3 formulas you could use. Which one you want to use? Cosine squared theta minus sine squared theta, because we've already calculated both of those. So cosine theta we knew from the very beginning to be 5/13, so this would be 5/13 squared minus, and what we just found out sine squared theta was? Right there. Oh, I'm sorry. Not right there. That's 2 theta. Right here. That was your sine theta, right? And what was that? Negative 12/13 squared. Okay? Well, 5/13 squared is what? Yeah, 169, just like we had it before. 25 over 169 minus, and what would this be? Negative 12 squared? Goodness, my pen keeps. Okay, let me get that back again. I can't can't get it back. Okay, one. Goodness gracious, this is aggravating. There we go. 144 over 169. And that difference is a negative. -25 minus 144. Negative 119 over 169. So there's your cosine 2 theta. Okay, we're going to have to go back and do some head scratching in a minute, but let's continue. How about the tangent 2 theta? You feel like a double angle formula? Let's not, okay? Because guess what we can do? As a quotient formula, ratio formula. Sine 2 theta over cosine 2 theta. Since we've already calculated both of those, that would be negative 120 over 169 over a negative 119 over 169. And that would be what? The minuses go out, the 169s go out, and that leaves you with almost 1. Not quite, just a tad over 1, 120 over 119. Right? Now, let's see if this makes sense. Okay? We already said this is your theta here. Just a little over 3 quadrants, right? Slightly more than 3 quadrants, right? So 2 theta would be slightly more than 6 quadrants, right? A little bit more slightly. So that'd be 1, 2, 3, 4, 5, 6. So you're somewhere down in here. This would be your 2 theta, right? Third quadrant. What's sine in the third quadrant? Negative. What's cosine in the third quadrant? Negative. What's tangent in the third quadrant? Positive. Yeah, that all looks like it works out pretty well. And we said it's, this much further than there. That looks like awfully close to your diagonal, doesn't it? Diagonal would be 1. This is 1.0 something or another. Awfully close to 1. So just beyond your identity function. Okay? In the third quadrant. Does that make sense? Yay or nay? Or sort of?
How did you get the 120 over 119?
Okay? I was lazy. And I said tangent 2 theta, sine 2 theta over cosine 2 theta. Here's sine 2 theta. Here's cosine 2 theta. Just put them over each other. And first I noticed that minus over minus is plus. And then the 169s, both the denominator is 169. You can multiply 169 over 169. Those go away, and that leaves you just 120. Or you could go back and use your tangent 2 theta formula. But then you'd have to figure out what your tangent is, and that's not hard either. The tangent is opposite over adjacent, which would be a minus 12 over 5. And then you could do everything you needed to do with that if you wanted to do it that way. I bet you get the same answer. Okay? Hopefully you would. If not, triggered something seriously wrong with trig. It all should work out. As long as you do it all right, it should work fine. So there was example 2. Any questions on that? Yay or nay? Okay. Let's clear our slide and go to example 3. Okay. Let's rewrite sine of 3x in terms of sine of x. Sine of 3x, ITO, that stands for in terms of sine of x. Uh-oh. SpaghettiOs, how are we going to do that? First, tell me one other way to write sine of 3x. What is 3x? Real simple. X plus, well, not quite that simple. Isn't 3x 1x plus 2x? Yay or nay? Okay. And do we know a sine sum formula? Sure we do. What is it?
Sine x times cosine 2x.
Cosine 2x. Is that all? Plus cosine x sine 2x. All right, we got that done. All right. Now we're going to want this in terms of sine x. There's a sine x. We're going to leave that alone. We like that right there. But let's write cosine 2x in terms of sine x. Remember, there are 3 ways to write cosine 2x. Let's write it in terms of sines. You remember what that one was?
Sine squared. 1 minus sine.
Yes, 1 minus sine squared x. Everybody remember that? No, 1 minus 2, wasn't it? 2 sine squared x.
Yes.
Okay? Make sure.
Yeah, you're right.
Okay. Plus, now I right now can't do anything about cosine x, so let's just write it down. I don't want it there, but I can't do anything with it. But I can write down what sine 2x is, and what's that?
2 sine x.
2 sine x. What'd you say? Cosine x. All right. Okay. So let's string this out and see what we get. There would be a sine x minus 2 sine cubed x, right? Distributing the sine x across there. Now let's do the same thing here with the cosine x plus well, actually all those 3 are terms, plus 2 sine x times cosine squared x. Right? Ha! I can write cosine squared x in terms of sine. Can't you? What would that be?
1 minus cosine, 1 minus sine squared.
Perfect. So you got a sine x minus 2 sine cubed x plus 2 sine x times 1 minus sine squared x. That's what you said, right? So let's distribute that across. This is your sine x minus 2 sine cubed x plus 2 sine x minus 2 sine cubed x. Did I do it right? Think so. Okay. Let's combine like terms. What do you get? Say again?
3 sin
3 sin
x
x
negative 4
minus 4 sin cube x. Oh, wow. Look at that. We did find sin 3x in terms strictly of sin x's. No cosines, no tangents, no anything else. Just no sin 2x's or 3x's, you know, just sin x's. And sure enough, that's what the book got as well. And guess what their checkpoint is? Do the same thing with cosine 3x and see what you get. All right. Now, before we go to the next slide, let's do a little backtracking, okay? We haven't ever done that, have we? Okay? And here's the backtracking I want us to do. Remember, we came up with two formulas that look pretty close to each other. One was our basic Pythagorean identity. What was that? Remind me of it.
sin squared x plus sin squared x.
Okay. I'm going to slightly rewrite that. Is that okay? Yes, tell me yes. Okay. I'm going to rewrite it as 1 is equal to cosine squared x plus sine squared x. That's the same thing, isn't it? Okay, just rearrange it. And what was the second one that sort of looked a little like that but different? No. Don't. Yeah, there is one like that, but let's go back to the first one. Cosine squared x minus sine squared x. Isn't it? Okay. Now, I'm going to ask you to do two things with that pair of identities, because those are true. Those are both identities. True for all values of x, right? Okay. Now, first thing I'm going to ask you to do is add these two together. And what would that give you? I'm going to start with cosine 2x. Cosine 2x plus 1 is equal to two of them, aren't there? 2 cosine squared x. And those add to 0, don't they? Yea or nay? Sine squared minus sine squared is 0, right? So, let's divide both sides of this by 2. And let's see what we got then. Cosine squared x is equal to, because here these go out, cosine 2x plus 1 over 2. My goodness, if we didn't have enough expressions for cosine 2x, here's another. Okay? Now, here's what this one's doing. You're going from a squared to a first power. Second power to first power. They call that a power-reducing formula. Yay. Okay. So you can step down a notch if you want to. Okay? The second thing I'm going to ask you to do with these two are subtract them. Okay? And if you subtract this one from that one, what do you get? 1 minus cosine 2x is equal to, I've already changed signs, so I'm adding now. Those go to 0, and you have 2 sine squared x. And if you divide both sides by 2, like we did before, here the 2's go out, and you wind up with sine squared x is equal to 1 minus cosine 2x over 2, which is another power reducing formula. Here we have another expression for sine squared x. 1 minus cosine 2x divided by 2. Or 1/2 of 1 minus cosine 2x. Parentheses. Those are what they call the power reducing formulas. Okay? Now, reverse those orders and then come up with a tangent squared x. What you reckon that would be? A quotient or ratio identity. Second? No. Quotient or ratio identity. What is tangent? Tangent x is sine over cosine. So this would be sine squared over cosine squared. It would be 1 minus cosine 2x over 2 over 1 plus cosine 2x over 2. And you can multiply and get rid of your 2's and have just simply 1 minus cosine 2x over 1 plus cosine 2x. There we have it. We have another expression for tangent squared x in terms and a power reducing from second power to both of those first power. So there are our 3 power reducing formulas. Okay? Do I sit down and memorize these? No, I usually remember how I got them. You know, that's pretty easy. Or I'll look them up. Okay? Or you can memorize them if you want to. But here they are in their writing, right here. The double angle formulas can be used to obtain the following power reducing formulas. It's actually the double angle formulas with the Pythagorean identity will produce these 3. Okay? There are times when we will use all 3 of those. In Cal 2, I think it is. Are all of you going on to Cal 2? Oh, you're only doing Cal 1? You're doing only Cal. Oh, you're not doing any?
No, this is the last one.
Huh?
This is my last one.
That's your last one.
I gotta go to Cal 3.
Oh, you got to go to Cal 3? Okay. I figured most of them did. What's your major that you need to?
Kinesiology.
Is what?
Kinesiology.
Okay.
Kinesiology.
Oh, kinesiology. Okay, yeah, that's right. Because you only need physics with trig, not with physics with calculus. What's that?
Science.
Yeah. 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 And are you going into physical therapy?
Trying to decide.
Okay. I had a nephew who was kinesiology major, and he went that way, so I just was making a guess. Okay. Now, here's example 4. Reducing a power. Hey, we might use a power reducing formula. Let's rewrite sine 4th x in terms of first powers of cosines of multiple angles. Whoa, I have it for squares. Can we do it for fourths? Let's see. Sine 4th x. I know a power reducing formula for square, but I don't for fourth. Do you? But how could we write that? Sine squared x times sine squared x. Excellent. Okay. And what was sine squared x in terms of cosine? Multiple power things of cosine. We just did it, right? Anyone remember? I know it was a long time ago. Cosine 2x, right, over 2 times 1 minus cosine 2x over 2. Okay? Let's take out the denominators and just make that 1/4 out front. Is that okay? And then what we have left is 1 minus 2 cosine 2x plus cosine squared 2x. Okay? We're almost there, but not quite. Why? It says in terms of first powers of cosines of multiple angles. That's the first power, that's the second power. So what must we do? Anybody? Any ideas?
Good.
Any ideas?
We like that. You write it as.
I think you may be close. What we want to do is reduce this square to a single power. Right? We have a cosine. Yeah.
The square root.
Okay.
The square root.
No, not that. Don't we have a power reducing formula for cosine squared? Didn't we just have it up there? In fact, hang tight. Oh, there it is. Okay? Cosine squared, that was u. Now we have 2x, right? So that would be 1 plus
2 cosine 2.
cosine
4.
4x over 2. So that last one would be, I'll put it in parentheses, 1 plus cosine 4x over 2. Do you agree? Got it? Okay. Now we got to mess with our fractions and denominators, so let's go with that. Let's multiply through the 1/4. So that's going to be a 1/4 minus 1/2 cosine 2x plus 1/4 times 1/2 there, that would be 1/8. And then multiply it through there, and that would be plus, yuck, cosine 4x over 8. Or maybe I should have just said 1/8. That probably would have been better. It doesn't matter. Okay, well here's a 1/4 plus a 1/8. I think that's going to come up to be 3/8 minus 1/2 cosine 2 theta plus 1/8 cosine 4 theta. Is that 4? How did I get thetas in there? Those are x's. Okay. All right. Now that's one way to do it. If I'm not mistaken, they factor out a 1/8 and have 3 minus 4 cosine 2x plus cosine 4x. or something like that. Let's see. Yeah, that's how they write it. Why, I'm not sure, but they did. Okay? What you think? Sure enough, we started with a sine fourth x and wound up with first powers of cosine multiple angles, 2x's and 4x's. Okay? Yep. So we reduced our powers pretty significantly. So let's erase this and see how they did it. I bet you it's very close to the same, maybe a few nuanced differences. Here's the first. Rather than writing as sine squared times sine squared, they wrote it as sine squared squared, which is what I was starting to do, but y'all said sine squared times sine squared. Sure, why not? So what you do then is 1 minus cosine 2x, that's what sine squared is, over 2, that's what it is, and then square that, which gave us the same answer of, they pulled out the 1/4, 1 minus 2 cosine 2x plus cosine squared 2x. You still got a squared term in there, so we need to do one more substitution, and that would be 1/4 times 1 minus 2 cosine 2x plus, and that cosine squared of 2x becomes 1 plus cosine 4x over 2. I'm losing it fast, folks. I don't know why. Thursday, end of the week, I just start running out of gas. Okay? So what they do now is distribute the 1/4 inside just like we did. 1/4 times 1 is 1/4. 1/4 times 2 is 1/2 cosine 2x. 1/4 times another 1/2 would be 1/8. And 1/4 times cosine 4x over 2, that would be 1/8 cosine 4x. They combine these two like terms, that gives you 3/8x, and then you have a minus 1/2 cosine 2x plus 1/8 cosine 4x, and then for some reason they factor out a 1/8, which is fine. And that pulling out the 1/8, and that leaves you a 3 here, minus 4 cosine 2x there, plus cosine 4x there. Same answer we got. Make sense? Okay. There is a checkpoint there. Rewriting tangent fourth x in terms of first powers of cosines of multiple angles. That could be a little more involved. Okay. Feel like time for another flashback, or do we have time?
3 minutes.
Okay. Don't think we're going to have time, but I'll start your flash and we'll finish it up next time. Here's where we're going to start. Okay? We're going to start with pretty close to what we left off before. Okay? Sine squared x is equal to 1 minus 2 cosine, is that right? It's 1 minus cosine, not 2 cosine. No. All these constants in there, I get them crossed up. Cosine 2x over 2. Check us out there and make sure that's right. I think it is, isn't it? Right?
Yeah, 1 minus cosine squared x over 2.
1 minus cosine 2x over. Sine squared is 1 minus cosine squared x. You wouldn't need it over 2.
Yeah, that's right.
Okay, got it? Okay. Now, if you take the square root of both sides, now we have, are we out of time yet? 1 minute? 2 minutes. All right. Yeah, we can do that. Take the square root of both sides, and that gives you sine x is equal to either plus or minus the square root of 1 minus cosine 2x over 2. That's 2 is in the denominator, in the radical. Okay? Well, here's something. What if this 2x were u, or not you or somebody else, u, and then this would be half a u, wouldn't it? Now we have a half angle formula. Sine of a half angle is either plus or minus 1 minus cosine of that angle over 2. So that is your half angle formula for sine. Okay? Now, what do we do with those plus or minuses? I don't understand. Where would they come into play?
Where you are on the...
Exactly, where you are on the unit circle. If you're in the top two, then you're plus. If you're in the bottom two, you're in the minus. Okay? Yeah, that determines that. Okay? And are we out of time now?
Yeah.
I was afraid of that. Okay, we'll pick up then next time with the second half angle formula, which is the cosine. Okay, we at least got the sine done. Okay, so we'll pick up with cosine, half angle cosine, which is very, 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 very similar to that. All right, homework exercises. Let's do just a couple of those, if I can find my markers here. Think you can do any of the odds 7 through 13. They're all at calcchat.com. 9's at CalcView. Do any of the odds 15 to 19. They're all at CalcChat. Do any of the odds 21 to 25. They're all, or 21 to, or 23. They're both at CalcChat. 21's at CalcView. Try doing 25 is at CalcChat. And try doing any of the odds 27 to 33. They're all at CalcChat. 27's at CalcView. Before you go, I've got one more thing. And then you can start maybe trying to do the half angle formula, but we just barely got started there. Here's my question to you. Are you at all interested, besides swinging back, at all interested in getting your test so you can start working on it, even though we're not through with 5.5? Not at all interested. Any of you? Not? I have one off just because I thought y'all would be eager beavers, but no. Okay. They'll be ready for you on Tuesday. Have a good weekend.
Yeah.